and the all sort, you can say temperature, everything. So you will be able to, if you have the system to deploy a anti-missile, then your anti-missile can accurately fire to the missile to explode in the air. Otherwise, if it misses also, it may create a problem. That means your anti-missile may not work properly, and the missile will also, so in very sensitive cases, the control system has a major role to act quickly and very accurately. So, in such cases, we require artificial intelligence based controllers like neural network control, fuzzy logic control, and many such controllers are there, which is helping nowadays for taking decisions. I can say tracking the path trajectory quickly and accurately. So, this is how one of the example that I have given. So, now we can take that how this control system with artificial intelligence based control system is helping in healthcare system, that we can discuss now. How this AI helps to control the breathing mechanism. So this is the topic that I want to come now, because the objective when I started my talk, the topic was basically a controller design to control the breathing mechanism. So basically, what is the breathing mechanism? We have inspiration and expiration. So I want to control the breathing mechanism. You might know that if someone cannot breathe properly or naturally, so how it happens? Basically, it happens in different problems. When we have a lungs condition problem, like we have asthma, pneumonia, chronic obstructive pulmonary disease, lung cancer. If we have some heart conditions like heart disease, heart attack, congestive heart failure, allergies, a life threatening allergic reaction, injuries, a broken rib, neck, chest wall, lung injuries, and some other condition may also create a situations where a patient or a human being cannot breathe properly or naturally, like anemia, anxiety, panic attack, carbon monoxide poisoning, low blood pressure. So these are the some cases where some medical conditions where human being, or I can say a patient, cannot breathe properly or naturally. In such situations, what to do? What how this AI is going to help us? Now we require a artificial breathing mechanism. So what we require, you sometimes you might have seen, we have respiratory system, artificial respiratory systems, that we call it as a ventilators. So whenever the patient is unable to breathe naturally, then we require some breathing mechanism, or I can say artificial respiratory system or a breathing mechanism to help the patient to breathe properly. So what is a ventilator? You can see that there is a ventilator which is connected to the patient, which is unable, the patient is unable to breathe naturally. So a ventilator is a type of breathing mechanism which provides a anti artificial ventilation. So I can say it gives a moving breathable air into and out of the lungs. That means it will create a pressure, and it will create a situations where the patient can breathe properly, and it also can breathe out properly. So this is what we call it as a ventilator system, or we can say artificial respiratory system. So this helps to deliver breaths to a patient which is physically unable to breathe or breathe properly. Now, we know that how this breathing mechanism or the breathing system, artificial breathing system or a respiratory system helped us in COVID-19. The importance of this ventilator was, is well known to everyone. It was happened to available to everybody in in many of the household, you know, basically household term now. So what is the importance of a ventilator? A ventilator applies positive and expiratory pressure, that we call it as a PEP, at the end of each breath to prevent the alveoli, that is called basically the teeny branches of air tubes in the lungs. You can able to see that this is our lung system. So in this lung system, you will be able to see that this teeny, branches of this air tubes, which is called alveoli. From this, it helps us to not to collapsing this one. It is required to control airway pressure to prevent lungs from the collapsing. So this the ventilator's pressure pattern must be synchronized with the patient attempts for respiration during the ventilation process. So if you can understand from this, I can say that whatever the artificial ventilation pattern that you want to provide it to the patient, it must satisfy the natural breathing pattern of the patient. So that means I cannot give him any amount of any volume of air or any pressure of air to a patient. What we can say that we it is ideally good whenever the the pressure and the volume of air that has to be given to the patient must follow the natural pattern of the patient's behavior. So this is how it is possible to provide the artificial ventilation system. So how to achieve this one? So this can be achieved, the synchronized ventilator pressure pattern with the patient's respiration pattern. So this is possible by synchronizing the ventilator pressure with the patient's respiration system. If it is synchronizes, the patient will not feel any such problem or any such difficulty in breathing through a artificial ventilator system. Otherwise, the patient may collapse because of the non synchronization of this breathing pattern. So how this is possible? So to development of pressure control mechanism for ventilator. If I want to control the pressure of the ventilation system, the pressure of the air to the ventilator to the patient, so it is possible that I can control the pressure and also the volume, both I can say. But this topic today that we are going to discuss is basically the control of the pressure control of this pressure control mechanism for the ventilator. So you can see that there is a feedback control strategy. So this is a feedback control strategy in our control system, or in, I can say, any of the in this world. Like like when we conduct a workshop, we give our feedback. At the same time, we require the participants feedback to improve ourselves. So everywhere, when as a faculty, when you are teaching to the students, you require the feedback of the student to improve the quality of teaching where the faculty. At the same time, the feedback of the faculty is also required to improvement in the students behavior. So this is how the feedback system works. When we require the output to the input for comparing and generating a error signal and reducing this error signal with a time span. And we this is also it is also required that how fast we will be able to reduce this error signal. So therefore, we have to design a controller, I can say additional device or a additional mechanism which will be helping or generating a control signal to the artificial ventilator in such a way that it can give a synchronized pattern of air flow to our lung system. That is what we expect. That means whatever the air that we want to inject to our lung system must follow the natural air breathing pattern. That is what I can say synchronization is required. So whatever the natural breathing pattern must be followed by the artificial ventilator. And for that reason, I require a control action from the controller, or I can say additional device which will control reduce the error signal. And I will be able to find out a synchronized breathing pattern or synchronized breathing pattern in case of a artificial ventilation system. This is how it is expected from this control mechanism, which is a feedback. So with respect to the time span, with respect to the time span with respect to the time span, we will be able to achieve this controlled. So this is in this research work what we have proposed a control strategy. Now, in this control strategy, let me explain you. This is what we have considered. We have considered a artificial ventilator. We have mathematically modeled that this artificial ventilator, which is a patient host blower driven mechanic ventilator, and we have mathematically modeled it. This mathematical model is basically mimicking the patient behavior with a hose blower driven ventilator. And we have designed, we have considered one controller, which is a very simple controller. This is a PID controller, proportional, integral, and derivative controller. You can see there are three parameters of this PID controller. One is KP, KI, and KD. Okay. Now you can see the all these three parameters like KP, KI, KD is obtained from a fuzzy type 2 inference system. So here we require a artificial intelligence model, that is a fuzzy inference model, which is a type 2. Okay, that will give you the output of that fuzzy type 2 inference system will give to this PID controller, to this all these gain parameters, that is your KP, KI, KD. Okay, now so you can see that error and change in error, basically the two inputs of this fuzzy type 2 inference system. And in this mechanism, in this proposed strategy, what we have done, we have considered the input membership functions for this error and change in error, and output membership functions for KP, KI, and KD. So you will find we have the membership functions whose ranges has to be optimized by a optimization algorithm. Here we have used a human conception optimization technique, or a optimizer technique, which is proposed in our laboratory. So that has been used for optimizing the range of the membership functions. So you can see that how the range of this membership function is optimized by this function, and in this way we will be able to receive or reduce this error signal, such that the control signal will be able to control the pressure of the artificial ventilator in such a way that it will act, or it will behave, or you can say it will act like a synchronized pattern of the natural breathing mechanism of a human being. So this is what the proposed control strategy. So now let me go one by one. Let us go to the patient modeling, how the mechanical ventilation model, what we have done. We have considered a patient hose blower driven ventilator. So we have considered a, so let me ask once again that whether am I correct? So am I audible and clear to all of you? Okay, okay. Thank you very much. Thank you very much for your attention. So so what we have considered a patient host blower driven mechanical ventilation system, and we from this mechanical modeling we have a system, and we have a host filter system and a patient. So all those, by considering all those parameters, we have designed a transfer function model. So this transfer function model is a second order model. We, after designing this model, then we let us come to the second part. Let us come to the second part. This is the second part, is your basically controller. So one by one I will explain how we have designed the whole thing. So the second part is basically a simple PID controller for the system. Now you can see that this is a PID controller which is having three parameters. One is KP, KI, KD, and these three parameters are coming from this fuzzy type 2 inference system. So you can see that the KP, KI, KD is coming from type 2 fuzzy inference system, which is having a input membership function and output membership function. And the input membership, basically the inputs are inputs to the fuzzy type 2 inference system are error and change in error. That means whatever the error signal that we are generating, every time we are generating some error signal which is given to as a input, one of the input to the type 2 fuzzy inference system. At the same time, we are differentiating the error and we are finding out the change of error. That is also the second input to the type 2 fuzzy inference system. Now, coming to the output membership functions. So there are three outputs of the type 2 fuzzy inference system. One is KP, KI, and KD. So these three inputs are designed with a fuzzy inference mechanism that I'm going to explain in our future. Now, basically, this is a fuzzy type 2 inference system. What is a fuzzy inference system? So I think you in our session one, Dr. Subudhi has Professor Subudhi has explained you what a fuzzy mechanism is. So I'm not going to the fundamental of this fuzzy mechanism. I think most of you be aware about this fuzzy mechanism. So this is a type 2 fuzzy mechanism. So in the difference between a type 1 fuzzy mechanism and type 2 mechanism is that it has only one membership function. That means the multiple membership functions are there, but it doesn't have a lower membership up, it doesn't have a lower membership function. But you can see that in case of a type 2 fuzzy mechanism, every membership function has a upper membership function, at the same time lower membership function, and upper membership function is also having, you can say, a maximum range and a minimum range. Similarly, for the lower membership function is also having maximum range and minimum range. So this is how you can say the type 2 fuzzy mechanism, the 5 to fuzzy membership has to be designed. So coming to the type 2 fuzzy mechanism, what we have considered six different types of membership function. One is negative large, negative medium, negative small, zero, positive small, positive medium. So we have considered only six. It is up to you how can you can improve or increase in your, to improve the accuracy also you can increase the number of membership function. But the constant is that if you are going to increase the number of membership function, it will be complex, at the same time it is time consuming, more time consuming. So therefore we have considered with six membership functions. So in case of a, you can say the input membership functions for error and change in error are also six member. In case of change in error also six members. Using this rule for the outputs KP, KI, KD, all those three outputs we have considered the same fuzzy rules for which is presented in this table. Whenever the error is negative large and change in error is negative large, the KP is negative large, at the same time KI is also negative large and KD is also negative large. So this is the fuzzy rule that we have proposed for this model. So next one is that now we have seen that in case of a type 2 fuzzy, what we have observed, uh, uh, that there are how many, the two input membership, three output membership, and each of the membership is a type 2 type 2 fuzzy membership function. So every membership is having a upper membership function and lower membership function. So now the range of that upper membership function and the lower membership function is basically a normally what we fuzzy designers or a control designers used to do, they used to set the range manually and fine tune the output. But in this approach, what we have done, we have considered a optimization technique where we have, using this optimization technique, what we have to do, the range of the fuzzy membership function has to be obtained, or I can say optimized. So now what we have considered a human conception optimization. So basically the human conception optimization is proposed by um, in our laboratory. We have proposed this one. So so let us know about this human conception optimization. Before going to the optimization details, so let me give you one very brief introduction to optimization problem. Basically optimization problem is everywhere, including mechanical engineering, electrical engineering, computer science engineering, economics, finance, anywhere, everywhere you find there is some problems with the optimization. That means I can say that If somebody is having a business, so what they require, they want to maximize the profit, minimize the loss. If I want to invest, build one house or a structure or a bridge or a road, I have to minimize the cost of expenditure invested for the bridge, for structural design. So there are so many aspects, you will find so many applications. I think infinite number of applications you will find in our everyday life where the optimization has an importance. So here we have developed an optimization algorithm by our laboratory. So this optimization technique is basically a human conception optimization. It is based on the biological principle of human conception process. The strategy pursued by the sperm is searching for the in the fallopian tube are modeled in this HCO, and we know that the best sperm which will meet the position of the egg will be the global solution of the algorithm. So this is how the human conception has inspired us to design a conception optimization approach. So what is the inspiration? So let us now go through this inspirations, how we are inspired. The human conception happens when the healthy sperm cell meets the egg in the fallopian tube. The process begins with the millions of sperm being released into the female reproductive tract. All sperm cells complete to fertilize an egg. In general, a single sperm is able to fertilize the egg in the fallopian tube. Among the millions of sperms, the population of the most capable sperm can only enter the cervix. The cervical fluid, which we call it as a mucus, it helps the spermatozoa swim through the uterus and the fallopian tube and meets the egg. The cervical cavity filters out the liquid called semen, which contains the sperm cell released into the vagina. Sperm use the variety of mechanism as they travel to the egg to fertilize. So this is basically how we are inspired to design or the mathematical model of this human conception strategy to design a optimization algorithm. So before going to the design of this algorithm, what is the let us know about the biomechanism behind the sperm fertilizations. So initially the sperm takes a random position in the vagina and stays inside the fluid called semen. According to the fitness of the sperm, a swarm of fittest sperm cell is capable to enter the cervix. During their journey to the egg, sperm perform several outstanding navigational tasks. The sperm tail that we call phlegm aids sperm swimming towards the egg by creating an irregular and oscillating beat pattern. Which, like, I think you can see that how the infinite numbers of sperm cell is entering to the fallopian tube, towards the fallopian tube, but the fittest sperm only able to meet with the egg for conception, while balancing the moment of force caused by the phlegm movements. The cell head rotates and exerts force against the cervical fluid to move forward. So how the you can see that the structure of the sperm, basically the tail of the sperm is basically called phlegm. It helps it swimming towards the egg. So how it does? The sperm cell moves the different hydrodynamic modes. So there are some hydrodynamic modes are there through which the sperm cell moves towards the egg. So what are these hydrodynamic modes? One is typical helical and hyperactivated, and you can say chiral ribbons. On the basis of the environmental conditions such as temperature and viscosity inside the female reproductive system, the sperm can collect physical and chemical information to identify the egg in the female genital system with the help of some mechanism. So there are three mechanisms. One is the rheotaxis and thermotaxis and chemotaxis. So in case of rheotaxis, the sperm orientation against the fluid to move upstream, that means it moves towards the upstream. But in thermotaxis, the sperm sense the temperature variation, that means in the reproductive system it swims against the temperature gradient in a higher temperature zone near the oviduct, that means it moves towards the higher temperature zone. In chemotaxis, it the movement of the cell up to a connect concentration gradient, that means to it takes the viscosity basically, the concentration gradient of the chemoattractant, and the sperm move towards the increasing chemical concentration. So it basically, it is the feature, the movement is basically based on the viscosity, and the thermotaxis is based on the temperature, and the rheotaxis is basically based on the upstream movement. So these are the basically three different mechanism by which the sperm moves towards the egg. So the active sperm use the stroke called hyperactivation to cross the barrier of cumulus cells are surrounding the egg. Now you can see that when it reaches to the egg, there is a barrier. We call it as a cumulus. So to you know move and to break the barrier and move to fertilize the egg, it has to go for a hyperactivation state. When if the sperm is unable to hyperactivate and move it to the to break the barrier to meet to the egg, it cannot conceive. That's why this hyperactivation has an importance to fertilize. A fraction of sperm is able to become hyperactive, so only a very one or two sperms are the flagger bit of the hyperactivated sperm have a high curvature and a wider amplitude, leading to a highly active motility. So such a pattern of the hyperactivity may create forces to facilitate sperm detachment and migration. So the sperm have to pass another barrier called as a zonal pellucida, a layer of egg. The sperm cell undergo a process called acrosome reaction, which involves an enzyme deposited at the head of the sperm. So it helps to break the zonal pellucida barrier to fertilize the egg. So these are the barriers it cross to fertilize the egg. So this is basically the biomechanism. Among the millions of sperm cells, only a single sperm cell is able to fertilize the mature egg in the challenging environment of the female reproductive system. The complete process is so challenging and unique that it motivates us to utilize the selection principle of winning sperm to develop a natural inspired meta-heuristic algorithm. So you can see that how challenging for a sperm to conceive or to fertilize an egg. So the whole process is a very inspiring. So from this inspiration, we are able to develop one nature inspired meta heuristic algorithm, which we call it as a you know uh, human conception optimization technique. So coming to the modeling of the mathematical modeling of the SCO, so initially there are millions of sperms injected to uh, uh, the rest the vagina. This concept will be used to find out the suitable initial fittest population from the randomly generated population of the initial positions. So what we have done, we have mathematically modeled the sperm cell. So we have for this reason we have we can generate x number of sperm cell, that we call it as x number of basically the variables, and the dimension depends on the what is the number of rows defines the dimension of the problem. So we have generated the sperm, that is basically the initial population, we can say in mathematics. When we talk about the human conception optimization, the mathematics behind to the inspiring, or you can say the mathematics for this generation of the initial population is just as the what it is replica to the sperm cell. So this is how we can generate the a matrix of initial population randomly. How we have generated, we have considered a maximum value and a minimum value of the variable. So within the maximum and minimum value, minimum value and maximum value, we have generated all the values in bit of the variables. So next, the what we have done, so we have in a fertile female, either the right or left ovary produces a mature egg for fertilization as shown in the figure. So the mucus fluid in the uterus helps the sperm cell swim towards the egg. So basically what we have done in the fallopian tube of the a fertile female, so it may in the right fallopian tube or in the left fallopian tube. So now So this, the movement of the egg must be maybe towards the left or towards the right. So by modeling this one, so what we have done during the evaluation of the sperm, what we have done, we have evaluated the uh, positions or the initial solutions. We have initial solutions, and the we have find out the fitness value of the with the initial solutions, which we call it as a fx. Now, as we know that for a fertile female, the egg may be generated in a left hand side or a right hand side. So we have model it as a opposition based learning. In this opposition based learning, what we have done, whatever the solution that we have randomly generated, we have created a opposition, that means the negative, or you can say the opposition values, by using this formula: x opposition is equal to a plus b minus x. And we have found out that whenever the fx is greater than fx opposition, it will consider the x, otherwise it will consider the opposition value of the x. So then what we have done, from this we have considered the fittest population. Out of this fittest population, we have set it with a, from the worst value to the best value. Sorry, best value to the worst value. We have and the corresponding x value is also formulated using the selection of the healthy population. So next one is that basically what I want to portray here is that how this human conception algorithm is mathematically modeled. This is how in left hand side I have explained how what is the biomechanism happening inside a human body, and how it has been in the right hand side, how we have modeled it. So the tail of the sperm creates a jerking like movement that helps the sperm move in the uterus, and the sperm cell starts following the curvature path caused by flagellar movement to the reach the egg. Now you can see that. So this is the sperm movement modeling. What we have done, you can say that the male reproductive cell, that is your sperm, has a single flagellum, or we can say tail. So to achieve the fertilization, the sperm needs to move up to the oviduct, and the sperm tail produces a distinctive jerky motion that pushes the head of the sperm backward. That means with this jerk motion, it move. That means towards back, it moves ahead sideways. While simultaneously propelling the sperm forward, the cell migrates through the fluid in the cervix by moving backward and sideways. The sperm cell is aided in its journey towards the egg by this combination of actions. They cannot swim backward. So they cannot swim backward. They can only move forward towards the cervix. So this is what the a 3D trajectory of the movement of the flagellum of the sperm cell. So the tail sperm can sense the concentration of the liquid in the reproductive system. According to that, it changes the position. So how it changes the position? Now you can see. So initially, so there is a human sperm uses the various sensing mechanism to gather physical or chemical signals to spot the egg. During the fertilization, I think we have discussed three different methods through which, or three different approaches to which it moves toward the cervix. So there are three different types of swimming guidance mechanism. One is thermotactis, rheotactis, and the chemotactis. So in this, basically, in our case, we have considered the rheotactis mechanism. So in the rheotactis mechanism, the mucus flow is towards the movement towards the upstream, and towards thermotactis is basically the temperature gradient. Rheotactis is basically the viscosity. So the so now, what in HCO algorithm, we have considered the rheotactis mechanism. We have not considered the thermotactis and the uh, uh, thermotactis and chemotactis. We have not considered. We have considered only rheotactis mechanism. So in this rheotactis mechanism, the position of the sperm is changing. Like we have mathematically modeled it, kj plus 1 is equal to kj. That means the position of the particle or position of the solution. So this is basically the sine of 2 pi. Basically, you can see the flagellar motions is basically a sinusoidal one. So we have model in such a way that the positions will change in a sinusoidal path. Then the sperm movement modeling for the position update of the sperm cell. So the sperm changes its position across the sinusoidal path on the basis of its own best positions. Now, what it does, so it basically it changes towards the best positions. That means it the best, basically the best position or optimal position is the position of the egg. That means whenever the sperm reaches to the egg, it gives us the best uh, solution. I can say that if you are searching for a value or searching for a variable for a objective function to minimize, so the solutions that we gives, the best solution is nothing but the position of the egg in case of a HCO algorithm. So how we will be able to get it? So what we can do, so the position is basically the k plus j plus 1 is the curvature path crossed by its ith sperm, is the sp best. I can say sp best is the present best position of the sperm, and si is the current position of the sperm. Sg best minus si is basically the global best. That means the complete best positions among its during the movement of the sperm towards the egg. So this is how the position or the updation of the sperm cell is being modeled mathematically. Now, during the movement, it uses the velocity profile. The velocity profile, the human spermatozoa can sense a flow of liquid and change the direction of their path against the flow. Because as we have considered only the rheotactis, it performs a positive rheotactis and the orients itself against an oncoming flow. So mucus flow, I can say, like sperm cell flow in fluid, can be described by the Pausley profile. So we have considered the movement will be Pausley profile, where the speed increases quadratically with the distance to the compartment boundary. In case of a HCO algorithm, we have designed Paussel velocity profile is used to model the velocity of the spark to update their position. So for the Paussel velocity profile, the velocity profile shows the amplitude of the velocity according to the position of the particle in a fluid. So according to the Paussel velocity profile, the velocity at a point called the specific radius in the fluid can be calculated by measuring the distance of the point from the center of the tube. At the specific radius, the velocity is formulated v is equal to p whole into s square minus r. With using this formula, the velocity, the partial velocity is basically calculated. Now, using this partial, velocity profile, what we have designed in case of a HCO algorithm, the fittest sperm is used to mimic the velocity profile. The velocity of the sperm in the current iteration is calculated by taking the sperm current position, that is chi I, in the healthy population and multiplying it by a fitness of f chi I. The center of the flow resembles the average position of the sperm with a fitness of the phi average phi value of this chi, or you can say average positions. The fitness level of the present global position is, this is the best value. So using this, we have calculated the average fitness, that is, and also we have calculated the velocity of the sperm, that is r is equal to the best position objective, the f of x best position minus f of chi I. R is basically f x average minus f xi, and L is basically f x best minus f x average. So this is how we will be able to find out the change of the um, uh, you know sperm positions using the velocity profile. Now, how this velocity will be updated? So the velocity will be after entering the cervix, the sperm cell gain to the initial velocity in the cervical fluid. In HCO, the sperm initially, I think, let me just have a. Am I audible? Am I audible and clear to you? Yes, yes. Okay. Thank you. Thank you. So the velocity is modeled according to the Poisson velocity tracking profile as presented in the figure. the position of the sperm cell in the current iteration will be it compared with the previous positions and updated accordingly. So we will find out the present best position and the global best by updating our positions of the sperm. So how can we update the velocity profile? In such space of the velocity sperm will be updated using the VI, using the formula VI is equal to omega 1 into the Vij minus plus Vij plus C1 into A1. So according to this, we will update the velocity profile. At the same time, the position of the sperm can be updated using this chi ij plus with chi j plus Vij, considering the Vij plus. So with this we will be able to update the position of the sperm and obtaining the best solution from the best solution. So when the position of the sperm is the position of the egg, that means it fertilizes. So whenever it fertilizes, that means whenever we will be finding out the best solution of a problem, then we will be able to find out the solutions. So using this we can opt now there is another thing that which happens. So basically in a optimization problem, we call it as a local stock problem. That means local minima or local maxima. So similarly in case of a the human bio mechanism, this also happen when the sperm cell overcome the barrier across the egg by a hyperactivation process. So they have to pass another barrier called Jonan pellucida. To pass such a barrier, the sperm must undergo a process called the acrosome reaction. So this is an enzyme deposited at the top of the sperm cell. So it has to be broken by the sperm cell to penetrate into the egg. So to model this one, what we have done, we have modeled the hyperactivation process. So in this hyperactivation process, what we have done, to cross the barrier of the cumulus, the sperm cell must be very specific stroke, which we call it as a hyperactivation. So if there is a this hyperactivation has to be modeled in such a way that if any of the solution is being stock in a local minima, there should be some changing of the position of the sperm such that it can have a better objective value or objective function. So this is how we have modeled. And in this modeling of this hyperactivation, what we have done, so x hyperactivated is equal to x best plus 1 plus this into sine 2 pi m1 into cos m2, and x global best also we have find out. That means the global best will be considered by the active hyperactivated value or the global best value. So whichever is best or whichever is better, then that has to be considered as the best value or a best solution for the problem. So this is how the hyperactivation process is also modeled in human conception optimization problem. Now I think the overall the whole thing has been a complete explanation for the how the human conception optimization algorithm is designed or a model, mathematically model. Now coming to our previous problem, what was the previous problem? If we can go back, we can see that we will go back just to yes, this is the, you can say, the how the optimization algorithm is used to optimize the membership function of the fuzzy type 2 system. So what we have used the mathematical SU algorithm for designing the optimal value of the objective function. What is the objective function here? For our case, the objective function is that error, you can say the integral time absolute difference between the targeted and the actual airway pressure has to be minimized. So what is the error here? Error is the desired airway pressure and the actual. I told you that means if a patient is, let us coming to the main problem, respiratory problem. That means the what the natural breathing mechanism of a patient. Okay, so natural pressure is having some, pressure is there for our breathing pattern, for our natural breathing pattern. And if we want to use a ventilator, it must also give a same pattern like a natural breathing pattern. That is how our objective is. So that's why the error is basically the natural or desired airway pressure and the actual airway pressure given by the So I want to reduce the error between these two has to be reduced. What are the constant here? I told you we have, now we have, you know, five membership functions, for input 2 and another 3 output, membership functions, and each membership function is having 6, each membership, error, having membership, 6 membership members are 6 membership functions are there in each, variable, each input variable. There are 6 membership function. Now every membership function is having some minimum value and a maximum value of the range for the variable. Now that is our constant for our objective function for the problem. Now you can see the initially what we have done, we have given the values of the membership functions initially we have given. Then the after, you can see after we have designed, you can see those membership functions are having a upper limb and minimum limb, and we got a optimal range of the membership functions. So you can see that A is for the membership function for the input variable, B is for the change in error, that is also another input variable, C is represented by a output variable, which is, I think, in first input variable is ranging from 0 point somewhere to 0.262148 and to 0.41408, and it is distributed equally similarly for the membership function for the second input, and for C is for the output variable, that is called KP, D is for the KD, and E is for the KI. So these are the numerical optimal ranges that we have. Initially we have given the values, but later on we have got the optimal ranges of the membership functions. So here also we got the membership functions, so optimal ranges we got. Now you can see that the simulation result that we have obtained, we have a, you can see that there is a desired trajectory. The desired trajectory is basically a square, a pulse pattern we have given. So the first one is basically the peak inspiratory pressure, and the lower one is basically positive and expiratory pressure, that PEP. And we can see that our proposed model is, which is represented by a green line, is following and having a better response than the existing, some of the existing results. So this is for the airway pressure. Okay. And similarly here, the we have done for the control signal, what control signal we have generated with the proposed controller, and some existing results. So here the error convergence curve for the optimal membership function for type 2 fuzzy PID controller for ventilator model. Here also the response of the proposed controller under external disturbance. That means if we have given some external disturbance in the system, then how it is going to handle by the controller. How it is going to handle by the controller. So this is how you can see that there is a nearly zero point 0.5 second we have generated a external disturbance pressure profile, and the our proposed controller, basically a fuzzy type 2 PID controller, is able to handle the uh, that disturbance correctly, and able to track the response of proposed controller under external disturbance also. So the behavior of the suggested controller when noise from the measurement is possible is present. Now we have also considered some worst situations. So we have considered a Gaussian noise, okay, with random standard deviation between 0 to 1. So during simulations, so, and we have also considered a Gaussian noise with random standard deviation of zero point 0.6. Then we have seen that the controller is able to track the PIP and PEP also. So similarly here, what we have considered, this is the control signal, the response of the proposed controller for different lung resistance and compliance. What we have done to test the robustness of the controller, what we have changed, we have done, we have changed the parameters of the parameters of the uh, lungs parameters. That means we have changed the patient. That means whether the controller is basically able to handle the different patient or not, that has to be, checked. So what is the possibility that we can do? What we can do, we have changed the lungs parameters. Using the lungs parameter, we have checked. This is also working fine with with some existing results. So then what we have done, so this is the response of the controller for time varying breathing patterns. So if there is a some patient is having some, time varying, that means with respect to time also the breathing pattern is changing, then also the controller is able to handle the situation. So then we did some comparative analysis with some existing results. We can some of the existing results were compared with the SCO fuzzy type 2 PID. It is found that it is maximum overshoot, the peak time, settling time, integral time, absolute error, variance, and norm of the control. In some of the case, in most of the cases, it is only the settling time is higher than the BCTO fuzzy PID and CCTO PID, but in otherwise it is better in some of the aspects. Peak also it is high, but settling time is maximum overshoot is better. So the complete work is published in a IEEE transaction on systems, man and cybernetics system. This is Devasis Acharya, is my PhD scholar. I think he has completed his PhD. So the person has developed both the human conception optimization under my guidance, at the same time type 2 fuzzy PID controller design also he has done for artificial mechanism. And there is a Nature publications, the a novel human conception optimizer for solving optimization problem is published in the Nature, the scientific report. So with this, these are the some of the references. uh, So with this, I want to end my session. If you have any query, please can ask. So I can open and I can unmute, but I think one by one, if you can speak, it will be good. If we will find any chaos, then so I think now you can unmute and ask me if you have any other, if you have any query, please. I request the participant if they are having any questions or query. Is it possible to measure the count and health of the sperm? It is possible, madam, but counting is not possible. Health through some medical process, we can count and find the we can do it. It's possible. Yes, Professor G Rasmi. Anybody want to ask any question? Am I audible? Yes. Okay. Thank you very much. I think